Hey there, we are in chapter 7 and we're looking at section 7-8. We've got one more section to go in this chapter and we're going to talk about inverse functions and relations. So you remember last time we were together, we discussed composite functions, f of g of x or g of f of x. That knowledge is going to be really required for you to understand what's happening in this section. So let's go ahead and talk about relations and functions and their inverses. So basically, inverse relations would be where a relation where the inputs and the outputs are switched. So you remember you can have a relation and you might have it as an ordered pair or as an XY axis or whatever. So I can talk about a relation, or as an XY table, I could talk about a relation as 1 is to 3, 4 is to 7, and 6 is to 12, let's say. And then the inverse relation would be switching those. Well, when x is 3, y is 1. When x is 7, y is 4. And when x is 12, y is 6. This would demonstrate an inverse relation, literally flipping the x and y. And so an inverse function is going to be the same thing, except inverse functions are going to have kind of a more stricter relationship, let's say. So for instance, if I have an inverse function, if I tell you that f of x and g of x are inverses of one another, first of all, I can write f of x and this g of x being its inverse, it's going to be the same as f inverse x. That's what this symbol means, f to kind of like the negative first power, but it's not to the negative first power. But it looks like it's to the negative first power, but it's not. This is not 1 over f of x, okay? So this is f inverse of x, and if g of x is the inverse of f of x, then this is what it really means, okay? That's the first thing. The second thing that we need to know, again, assuming that f of x and g of x are inverses of one another, you're going to get that f inverse, or f of g of x, when I compose these two inverse functions, my answer will be x. And it doesn't matter the order in which I compose them. So I can do g of f of x or f of g of x, and my answer still should be x. And we'll talk about the technique from going from one function to figuring out what its inverse in our discussion today. And then there's this idea of one-to-one functions that we need to talk about. And so one-to-one functions are functions such that what they look like, let's do what they look like first. They might look something like this. So for every x value, there's exactly one y value, and for every y value, there's exactly one x value. So instead of the function just passing the vertical line test, which we know defines it as a function, it also passes the horizontal line test, meaning every horizontal line that you draw over the graph only hits the graph at one time. So what that tells me is that not only for each x value there's one y value, but for each y value there's one x value. Let me show you an example, and you'll see this in our discussion of a situation that a function that's a function but is not one-to-one. So you can see this parabola is definitely a function, passes the vertical line test. But when we throw in the horizontal line test, we see that for the most part, every horizontal line is going to hit 2 points. That means, yes, for each x, there's only one y, but for each y, there could be 2 x values. This is not a one-to-one function, though it's a function. One-to-one functions will have an inverse function. Functions that are not one-to-one will not have an inverse function. And without us modifying it a little bit, we'll have to say, oh, we're only going to take the inverse of this function from here to here, such that we're dealing with a part of the function that is one-to-one. We'll talk about that soon too. So let's take a look at example 1. Here in example 1, we're asked to find an inverse relation. So we're given that the ordered pairs of this relation are given as follows: 2, 1, 5, 1, and 2, negative 4. Are the coordinates of the vertices of these are the coordinates of the vertices of a right triangle. We're going to find the inverse of this relation and determine whether the resulting ordered pairs are also vertices of a right triangle. Simple? Let's see. So here is the original relation. I'm going to highlight it in this purple color. And the inverse, I think you would know at this point, right? Don't use that. The inverse would be the set of all switched ordered pairs. So 1, 2, 1, 5, and -4, 2. Since we're talking about an inverse relation, I'm not going to point out that this couldn't be a function because we've got 1 to 2 and 1 to 5. They said relation, so we're cool. So this is an inverse relation. These guys have an inverse relation here. And I'll highlight this one in green. And so the next thing we're supposed to do is to see if we're going to actually get an ordered right triangle when we graph it. Okay, so I've taken the liberty of plotting both of these, both of the sets of points from the relation, and I'm drawing the lines. And yeah, we do actually get a right angle triangle for each. And I know these triangles don't look like they're the same size, but they should be if I numbered my axes in a more consistent way, and I didn't do a great job. But what I want you to see is that the relation is reflected over this y equals x line. These two relations are reflected over the y equals x line, and that is what you will always find when you're dealing with inverse functions or inverse relations. You're going to have one will be reflected over the y equals x line. Think about it. Remember, y equals x is where y and x are equal. And what's happening with the x's and y's in a relation we're finding the inverse? We're switching them. So it kind of makes a sort of symmetrical sense that when you switch the y and x value, you're going to be on the opposite side of the y equals x line. Let's look at the next example. Here in this example, what we're called to do is to figure out how to find an inverse function. And so the way we do that is pretty cool. We find the inverse function by first rewriting this out of function notation, writing it as y is equal to x plus 6 over 2. And this is the f of x function. The f inverse function, right? The inverse, what we do is we take the x and the y and we switch them. So we write x is equal to y plus 6 over 2, okay? So that's this situation here. This is what we do. We take it. We take the same function, we rewrite it in terms of y, and that's what the f of x is. But the f inverse of x is when we switch y and x. And now what we're going to do is solve for y. So to solve for y, we need to get y by itself. We're going to multiply both sides of our equation by 2. We get 2x is equal to y plus 6. And then we're going to subtract 6 on both sides to get, and I'm going to change the order of I'm writing this. Check it out. Y is equal to 2x minus 6. You get that if I subtracted 6 on both sides, I get 2x minus 6, and I just brought the other ones together over here. This is just a regular equation, all right? And then the next thing I'm going to do is replace the y with f inverse of x, because that's what I've created. So 2x minus 6 is f inverse of x is 2x minus 6 when f of x is equal to x plus 6 over 2. So graph the inverse and its function. Let's go ahead and take our time and do that. And so I wouldn't take up all the time in the world. I ended up just graphing it myself here. So the blue function is the original one, and I graphed it the way you would any linear function by recognizing that the y-intercept would be 3 and that the slope would be 1/2. I started at 3 and I went up 1 over 2, up 1 over 2. Here, y-intercept being -6 and my slope is 2, I go up 2 over 1, up 2 over 1, and I get this graph. And what we're going to realize is that the y equals x line is still honored here, where the graphs are reflections of each other over the y equals x line, which is also kind of confirmation that you have indeed done it correctly, that you found the inverse. So couple things about inverse functions. We talked about this before. When you compose them, f of g of x has to give you x and g of f of x has to give you x. We call this, it has to create like an identity function. If you think about identity, property of equality, I don't know if we talked about that in our class, but you may have heard about it in geometry. But anyway, identity property is basically, you know, what do you see when you get in the mirror yourself? So if Dion stands and looks in the mirror, she sees Dion. If x is put into the function, x comes out, therefore it's an identity. And so let's get back to the, I don't know why I'm here. I don't know what happened, children. Let's see. Okay, so that's what's happening there. That's the information they're giving us. And so now we're going to verify algebraically, I believe, determine whether these two guys are inverses of one another. So remember, if f of x and g of x are inverses of one another, right, we know that, let me write it this way, we know that f of g of x has to give me x, and at the same time, g of f of x has to give me x as well. So let's go ahead and compose these two functions. So f of g of x, let's do that first. F of x is kind of the framework function. So we're going to put 5, or let me think, how should I do this? F of g of x, let's do it like that. F of g of x is equal to 5 times something plus 10. What's that something? G of x. What is g of x? Let's rewrite it then. We know that g of x is that. So 5 times 1/5 x minus 2 plus 10. Take a moment to breathe it in. Make sure it makes sense to you. F provides the framework. G of x provides the thing we're substituting. What is g of x? It is 1/5 x minus 2. Now I'm going to go on and do my distributive property. When I do that, I get x minus, sorry about that, minus 10. You get that? 5 times 1/5 is just 1 or 1x, and then 5 times that -2 is that -10, plus 10 is going to give me x. So far, so good. Let's see if it works the other way. So now we're doing g of f of x, and we know that g of x is 1/5 times the x value, or whatever we're going to plug in there. What are we plugging in there? We are plugging in f of x. What is f of x? Let's rewrite it such that we have f of x in there. So we have 5x plus 10 minus 2. And so now I'm going to continue through the process. I'm going to distribute this through, and I get x, because 1/5 of 5 gives me x, and 1/5 of 10 gives me 2. So I have 1/5 of 5x gives me x, not 1/5 of 5 gives me x. That's crazy talk. So x plus 2 minus 2. And now I'm going to join these guys together, swoop delicious. And oh yeah, I got it again. So I have confirmed that these two functions are indeed inverses of one another, because when I compose them in either direction, I got x back, which is what we want. Finally, the text, the authors of your text give you this idea and kind of leaves you with this closing thought without really an example, which is okay. Just so you know, and we talked about it earlier, when the inverse of a function, when the inverse of a function is a function, then the original function is said to be 1-to-1. To determine if the inverse of a function is a function, you can use the horizontal line test. So let's think about it. I know we did this before. Let's look at this graph right here. If we think about the y equals x line, which is right here, and I were to reflect this over the y equals x line, I would get this green function that I'm going to kind of draw in here and see if it makes sense to you. 1, 2, 3, 4, and then what is that? So it would do like this, right? So you'd get this as the inverse. But this is not a function, right? It fails the vertical line test. So every function doesn't give us a function when we find its inverse. Every function doesn't give us a function when we find its inverse. So to determine if the inverse of a function will be a function, that original function has to be 1-to-1, meaning for each x value, there's a y value, and for each y value, there's only one x value. You can see our parabola fails it. We talked about it before, earlier in the video. Our parabola fails because when when y is equal to 1, x could be either this value here or this value here. It's not 1-to-1. How can we check to see if something's 1-to-1 using a graphical method? If you have a function, it already passed the vertical line test, we use the horizontal line test to determine if it's 1-to-1. And looking at the blue function, that original function, we see that it's 1-to-1 because no horizontal line will hit it twice. Looking at this blue function, if I draw these horizontal lines, you see that it hits it twice and all the time. All right? So that's the concept that you might be asked to kind of consider a little bit deeper in the homework assignment. I hope this made sense. Let me know if there's anything or any help that I can give you. I look forward to talking to you and seeing you soon. Take care, sweeties.